So this morning we're going to talk about the idea of an atom and something called an isotope, and then also how we determine an actual element on the periodic table's average atomic mass. So the first thing that we need to remember is, what is the difference? Or we need to ask ourselves, rather, what is the difference between atomic number and atomic mass? If you recall, atomic number was defined as the number of protons an atom has and the atomic mass is defined as the protons plus the number of neutrons an atom has in the nucleus. So we need to kind of keep that in mind. So let's specifically talk about the number of protons. So what would happen if you change the number of protons in an atom? Well, if you take a look on the periodic table, which atom has 6 protons? Well, according to the periodic table, that would be carbon. And which atom has 7 protons? Well, if you look on the periodic table, that would be nitrogen. Okay, so what happens when you change the number of protons? Well, the mass and the element change. So the element gets heavier and the element becomes a new element altogether. So what happens, so what changes if you change the number of neutrons in an atom? Well, before we answer that question, let me ask you another question. How do you find an atom's mass number? So hopefully you'll remember that mass number. Oh, let's do it this way. Hopefully you'll remember that mass number equals protons plus neutrons. So we just need to keep that in mind. So if we have an atom, like, say, carbon, so I'm going to say carbon, and another atom of carbon, and I say that there are, in the first atom of carbon, there are something like protons are equal to 6, and protons are still equal to 6, and the, let's see, the electrons, the electrons are equal to 6, and the electrons are equal to 6. But if I said that the neutrons were equal to 6 here, and the neutrons were equal to 7 here, what we would end up with is if we looked at the mass number, we'd take, in the case of the first one, 6 plus 6 would be carbon 12. And in the case of the second one, it would be carbon 13. And so what we really are noticing here is that the mass number changes. But nothing else does. So the number of protons is the same, the number of electrons is the same, but the mass number changes. This is a new concept that we are going to refer to as an isotope. An isotope are atoms of the same element remember, that means same atomic number. That have different mass numbers. Okay, so that's what an isotope is. To go further, just a little bit, here I have 1, 2, 3, 4, 5 different isotopes of carbon. And we're going to talk about this in a little bit more detail on the following slides. But what I really need you to understand here is that some of these are stable, which means that they're not going to do very much, and some of them are incredibly radioactive, which means they give off energy in some way, shape, or form to become more stable. So we're going to talk about these in greater detail. So here we have carbon 11. When I'm looking at carbon 11, I know that the mass number is 11 because that told me so. But to support that, I'm going to count the number of protons. So 1, 2, 3, 4, 5, 6. So that's 6 protons. And in terms of neutrons, I'm going to go 1, 2, 3, 4, 5. So that's 5. So, and again, our protons, or our electrons still, will still equal 6. 1, 2, 3, 4, 5, 6. So what we have here is we have the first isotope of carbon. Moving forward, we know that this is another carbon atom, and in this particular case, I'm being told that the mass number is 12, and I'm going to count the number of protons, 1, 2, 3, 4, 5, 6. That hasn't changed. The number of neutrons, though, is 1, 2, 3, 4, 5, 6. That has changed since the last one, so that gives me a mass number of 12, 6 plus 6. Note that the number of electrons is also still 6. So the only thing that's changing is the number of neutrons. Let's take a look at carbon 13. Carbon 13 has a mass number of 13. Let's count to support that. 1, 2, 3, 4, 5, 6. 6 protons. And neutrons would be 1, 2, 3, 4, 5, 6, 7. 7 neutrons. And the number of electrons, still going to count them out. 1, 2, 3, 4, 5, 6 are still 6. So again, 6 plus 7 is 13, which supports its mass number. And then lastly, the last one we're going to talk about here is carbon 14, which has a mass number of 14. And we're going to count our protons, 1, 2, 3, 4, 5, 6, 6 protons. The number of neutrons is 1, 2, 3, 4, 5, 6, 7, 8. 8. Still, the number of electrons is still 6. So the big deal about these isotopes is that the number of neutrons change. Everything else behaves the same, or is the same, and that's important to remember. Now, this atomic notation, you're going to have to use this atomic notation on your homework. And the way that it works is that we put the mass number on top. So we put our mass number on top and our atomic number on the bottom, protons, right? So when I go to when I see that, for an example, would be something like oxygen. Oxygen has a mass number of 17, okay? and an atomic number of 8. Well, the atomic number still tells me protons, so that gives me 6 protons, which will also give me 6 electrons. In order for me to figure out my number of neutrons, I will take mass number minus protons. So in this case, it would be 17 minus 6. Nope, I lied, not 6. Ooh, geez, I got carried away here. Minus 8, which would give me a grand total of 17 minus 8 is 9. So the number of neutrons is 9, and I need to fix this. I screwed this up. I don't know what I was thinking. So this should be 8, and this should be 8. So, and the element is still oxygen. Okay, so this is the let's see, protons plus neutrons is our mass number. Okay, you're going to need to use that later. Now, element abundance. This is a little bit tricky. We have to talk about this here. So, element abundance, what we need to understand is that some isotopes in nature exist more frequently in nature than others. And we call that element abundance. Okay, so element abundance is described in percentages, but when we use them in a calculation, when we use them to calculate average atomic mass, on the periodic table, we have to convert the percentage to a decimal. So we definitely have to convert a percentage to a decimal. So we'll talk about how to do that in a few minutes. Now, the other thing we need to keep track of, oops, that's not right, is the average atomic mass listed on the periodic table is a weighted average much like your grade. Man, that is awful. Much like your grade. So it's a weighted average for all of the isotopes of that element. So, there's a formula for it, and the formula is average atomic mass equals, and I'm going to put brackets for a minute, so abundance of element A, or isotope A, times mass number of isotope A, close that bracket, plus abundance of isotope B times mass number of isotope B, put that in the brackets, plus dot, dot, dot. Now that dot, dot, dot means that some elements will have more than one or more than two isotopes. So that means that we can just keep adding them. So let me show you how it works. So here's an example that you might see on your homework or a test or whatever. So if you looked at a sample of 100 chlorine atoms, we're told that 76% were chlorine 35 and that 24% were chlorine 37. Calculate the average atomic mass. So we're going to get our formula set up here. So we're going to take average atomic mass, and that's going to be equal to percent abundance of chlorine 35 times mass number of chlorine 35 plus percent abundance of chlorine 37 times mass number chlorine 37 okay, and since there's only two isotopes, I don't have to go any further. So average atomic mass when I go to plug things in, I know that I've been told that it's for chlorine 35, it's 76%. Well, 76% divided by 100 gives me 0.76 as a decimal. So 0.76, and I'm going to bring my mass number for chlorine 35 down, which is 35, plus, so here's my 24%. So if I take 24% divided by 100, I get 0.24. So that's my decimal there. So it's going to be 0.24 times the mass number, which is 37. And then I'm going to continue going further, and when I multiply this out, okay, I get an average atomic mass equal to, well, 0.76 times 35 is 26.6 plus 0.24 times 37 is roughly 8.9. We're just going to always go to like one decimal place, or a tenth rather. And then when I add all that business together, 26.6 plus 8.9, I get an average atomic mass of 35.5. And if you look at the periodic table, you will see that it says 35.453, I believe. Let me take a look. I can't remember. Yeah, 35.45, which is really, really close. So that's how we go ahead and calculate the average atomic mass. Now, your homework tonight is going to be worksheet number 3. It is a two-sider, and you'll have a couple of problems to calculate the average atomic mass on, and a table to fill in. So good luck with that, and we will check homework in tomorrow.